solid phase sonosensitization in polymeric media, using hydroxyapatite and calcium substituted theraphthol. In this work, we study solid phase sonosensitization in polymeric media, using hydroxyapatite and calcium substituted theraphthol. We define solid phase sonosensitization as the enhancement of the effects of ultrasound on biopolymer systems, modified by aggregates of nanoparticles. This effect is associated with the additional release of acoustic energy in regions where these aggregates are localized. The aggregates differ in their physicochemical properties from the surrounding biopolymer structures and therefore significantly change the response of the system to ultrasound exposure. They locally increase the absorption of ultrasound energy. At the same time, solid phase modifiers can localize acoustic energy within a volume determined by the size of the aggregates. This volume can be significantly smaller than the wavelength of the ultrasound. In a tumor, the formation of nanoparticles and their aggregates can be promoted by biochemical features associated with tumor growth, including a low pH and an increased concentration of calcium ions in the intercellular fluid. The additional release of acoustic energy in these regions may contribute to tumor cell death or slow tumor growth. We refer to the phenomena underlying this approach as solid phase sonosensitization, and the nanoparticles and their aggregates as solid phase sonosensitizers. The aim of this work was to determine how the polymer matrix affects the localization and morphology of solid phase modifiers in model systems, and to evaluate the temperature and cavitation effects of the acoustic field in modified gel systems. For the model systems, we use polyacrylamide and agarose polymer matrices. The modifiers were iron hydroxide, the calcium salt of theraphthol, and hydroxyapatite. Theraphthol, which is the octasodium salt of cobalt octa-4, 5-carboxyphthalocyanine, is non-toxic and highly soluble in water. Its acidic forms and calcium salts are insoluble in water, and in some tumors, theraphthol can form a solid phase. Ultrasonic irradiation was performed at frequencies of 0.88 MHz and 2.64 MHz, with intensities of up to 3 watts per square centimetre. Cavitation intensity was evaluated using a cavitometer. The device records broadband acoustic noise in the frequency range from 2 to 10 MHz, using a broadband hydrophone. Temperature effects in the modified gel bodies were evaluated using a pyrometer. The polymer samples were modified by 2 methods. The first was counter-diffusion of reagents, forming a poorly soluble compound inside a pre-synthesized gel. The second was the introduction of solid modifiers during gel synthesis. Counter-diffusion provides a model for the formation of solid phase sonosensitizers under conditions associated with metabolic atopism in tumor tissue. It is also useful for studying the interaction between the solid phase and the polymer matrix. Analysis of the samples modified by counter-diffusion revealed 2 distinct types of solid phase localization. In the case of theraphthol, the aggregated phase of its calcium salt was localized on individual elements of the agarose matrix. These elements act as nucleation centers for the solid phase. In contrast, in the polyacrylamide gel modified with iron hydroxide, structurally distinguishable inclusions were not observed. This indicates a high degree of dispersion and a relatively uniform distribution of iron hydroxide throughout the elements of the polymer matrix. The presence of these 2 localization patterns suggests that their acoustic effects can differ substantially. This is particularly important for temperature effects. The temperature curves shown here demonstrate the dynamics of temperature increase during ultrasound exposure of agarose hydrogels, modified with calcium substituted theraphthol and iron hydroxide. The samples contained the same amount of modifier, but were synthesized using different methods. The sample modified by counter-diffusion showed a faster temperature increase, as well as a higher equilibrium temperature. It should also be noted that modification of the gel with iron hydroxide decreased ultrasound absorption. This may be related to changes in the mechanical properties of the polymer network. The highly dispersed solid phase becomes incorporated into the network and changes its viscoelastic characteristics. The graph on the right shows the corresponding cavitation measurements. At an acoustic intensity of 2 watts per square centimetre, the signal recorded from the modified hydrogel was more than 4 times higher than the signal from the unmodified gel. This indicates that the conditions for the initiation and development of cavitation are substantially more favourable in the modified gel. The aggregates may act as generators of cavitation nuclei because of their internal structure, including movable pores, curved contacts, and the specific state of the medium within the aggregates. Finally, we examine the combined effect of ultrasound and theraphthol using bacteria as a model system. When theraphthol solution was introduced into a suspension of bacterial cells of Escherichia coli, the formation of a solid phase of the calcium salt was observed. This solid phase was localized most likely on the surface of the bacterial cells. Ultrasound exposure of bacteria in close contact with the calcium salt of theraphthol resulted in a loss of bacterial viability. A noticeable and reproducible effect was observed at ultrasound intensities from 0.6 to 2.0 watts per square centimetre, with theraphthol concentrations in the range of 10 to the -4th to 10 to the -5th molar. As shown in these images, ultrasound exposure in the presence of theraphthol produces changes in the shape of the bacteria and destruction of their membranes. To conclude, 2 types of localization of solid phase modifiers were demonstrated in hydrogel media using scanning electron microscopy. The first type consists of highly dispersed nanostructures distributed relatively uniformly along the strands of the polymer matrix. The second consists of aggregates localized at individual centers within the matrix. The greatest acoustic effect was observed in systems where the modifiers were localized on individual elements of the matrix volume. These systems were obtained using the counter-diffusion method.